Love him or hate him, Sir Isaac Newton was one of the founding fathers of our modern understanding of physics and motion. He was an English physicist and mathematician who created laws to help us understand them. The first law states that an object in motion will stay in motion and an object at rest will stay at rest unless acted upon by an unbalanced force. So, for example, say you have this here cardboard box. If I set it down here and nothing is touching it, then this happens. Now, let's look at the other side of this first law. An object that is in motion will stay in motion unless acted upon by an unbalanced force. Let's say you have a basketball. What happens when you roll it on this concrete? Now, let's analyze what just happened. Once the basketball left my hand, it rolled across the pavement and hit the grass, right? Well, there's more at play here. While the basketball sped up from the 0 miles an hour it was going while sitting in my hand, it also gradually slowed down while rolling due to 3 different forces: friction, gravity, and air resistance. Friction is the resistance to motion when 2 objects come in contact with each other. See how the ground is really tough? This causes a type of friction between the basketball and the concrete. Another way we can see this is if we replace somewhat smooth leveled ground with grass. Okay, so we rolled the basketball on concrete, because concrete, while it is rough, it's relatively smooth. But with grass, you see that all the little pieces of grass cause a type of friction that eventually slows the volleyball down enough to a complete stop. Now, let's look at our next force at play. Gravity. Gravity is the attraction that 2 objects have on one another. Alright, so this means if you throw this up, then Earth's attraction should pull it back down to the ground. So go ahead and do it. Take quick note that there are 2 factors that directly affect gravity: mass and distance. The more mass each object has, the more gravitational pull. For example, the Earth and the Moon both have a gravitational pull on each other. The Earth causes the Moon to rotate around it, and the Moon causes Earth's tides in the ocean. The closer each object is to one another, the more gravity is experienced. An example of this is the Sun has a more gravitational pull on Earth than Jupiter does. Now, let's talk about air resistance. Air resistance is the resistance an object feels when traveling through the air. There are 3 main factors of air resistance: speed, shape, and size. To put it in brief terms, if you have this normal flat piece of printer paper, and you throw it, see, it's so flat, the air catches it, and it just kind of pulls it around, and it ended up going in the opposite direction that you threw it. But if you have this more aerodynamic sheet of paper, you throw it, it goes a little bit further than what this did. Thus, you have better results. Alright, before we move on to the second law, there's one last thing to keep in mind about the first law, and that's inertia. Inertia is the tendency of an object to resist changing in motion. The more mass an object has, the greater inertia. With Newton's first law out of the way, let's discuss his second law. Newton's second law states that a net force acting on an object causes the object to accelerate in the direction of the net force. This is the formula used to solve for force. Force equals mass times acceleration, where F is force, M is mass, and A is acceleration. It's also important to note that the more mass an object has, the more force is required to move it. This is also why it's easier to move a little Hot Wheels car compared to moving a 3-ton SUV. Keep this in mind, however, there's also a difference between mass and weight. Mass is the amount of matter in an object, and weight is the force of gravity on an object. If you take this large car and put it on the Moon, it would obviously weigh differently. This is because of gravity's force on this object. It weighs 3 tons on Earth, but on the Moon it would only weigh 1/6 of the original weight. Mass, however, would stay the same regardless of what planet you're on. If this car weighed only 1,000 pounds on the Moon and 3 tons on Earth, it still had the same mass in both locations. And finally, Newton's third law of motion. For every action, there's an equal and opposite reaction. This is where we talk about momentum. The formula for solving momentum is momentum equals mass times velocity. This one is confusing because P represents momentum, M represents mass, not momentum, and V represents velocity. Okay, to look at this. If we roll this basket, or this... Alright, to look at this. If we roll this volleyball into these here boxes, the boxes... Therefore, if we roll this bouncy ball... Stop! I'm gonna call it a volleyball.
I cannot myself.
Therefore, if we roll this ball into the boxes, we should...
What is so funny?
Stop recording. Okay, therefore, if you roll this bouncy ball, you should see the boxes fall over due to the transfer of momentum. So go ahead and roll these. Therefore, if you roll this ball down this little slope and you hit the boxes, the momentum should transfer and knock the boxes over. So go ahead and do that for us. Alright, you've lost your... Therefore, if you roll this ball into the boxes, you should see the boxes fall over due to the transfer of momentum. So let's go ahead and see that. Okay, if you take this, and then there's that car that ruins the entire shot. Therefore, if you take this ball and roll it into the boxes, the transfer of momentum should... Are you kidding me? Ball, boxes, momentum. Don't. Ball, boxes, momentum. Ball, boxes, momentum. Momentum! As the ball hit the boxes, the transfer of momentum caused the boxes to fall over and the ball to virtually stop. Hopefully you have learned something about Newton's 3 laws of motions and or have solidified previous knowledge of these. Anyways, I'm Daily Bratwell, signing out. Peace.